Before we move on to talking about specific types of electrodes, first of all, there's one mistake I had in this equation here. This should be positive instead of negative. It depends on the specific type of electrode, but with the equation that I had above, since the concentration of the outer was in the denominator, that would lead to a change in sign. So it should go from negative to positive. So just one small thing. The other thing I wanted to mention, that I did mention briefly, is the idea of interference. And this is probably the main issue with ion selective electrodes, is that while they are mostly selective, they do respond to other ions besides the thing you're trying to measure. And this is something we can quantify and keep track of, and if we know that these interfering ions are present, we can either try and get rid of them, or if we know how much they interfere, we can see if it's an issue depending on the concentrations that we're measuring. And so the way this is kept track of quantitatively is with what are known as selectivity coefficients. And these are usually provided by the manufacturer of the electrode. They tell you that there are interferences from these specific things, and they give you these selectivity coefficients. So these are defined as, they're given the symbol K, A, comma, X in your book. Let me write this POT here for potentiometry. And this is equal to the response to X, which is our interfering species, divided by the response to A, which is our analyte. So again, just to specify here again, A is analyte, X is the interfering species. Okay, so what this means is ideally we want this to be a small number, right? So so we want small k. And that would mean that our response to X is much, much less than a response to A. So even if there's a fair amount of X that's present in our solution, it won't interfere with our response to A. And what this is going to look like in practice is we will get a potential that is that looks like there's more of our analyte present than what is actually there. So right, so K equals 1, that would mean equal response to both species. And ideally we want K, like 10 to the negative something, right? You can even have possibly selectivity coefficients that are larger than 1, where you actually have a higher response to the interfering species than your analyte that you're interested in. So using this definition, we can rewrite what our response that we'll actually measure from our potential. E will be equal to K plus or minus, depending on the type of electrode, 0.05916 volts, again assuming 25 degrees Celsius, divided by the charge of A. All right, so this is going to be based on the charge of A is going to factor in here, and then log of the activity of A, which is this is our normal thing right here, concentration of A if we're ignoring activity coefficients, plus the response due to any interfering species. So we add up all the interfering species for all of our X. This will be our selectivity coefficient times whatever the activity of X is. So that'll basically, our concentration will appear to be higher than it actually is. And so this is how we mathematically can represent this, and this allows us to determine if we know roughly the concentration of our interfering species and what concentration we expect for our analyte, it can give us an idea of whether this is going to be a significant effect and that we need to worry about, or if we can ignore the interfering species. Of course, one way to get around this, right, the presence of interfering species, is to use a standard addition, because this interfering species is a matrix effect, right? It's something that's present in the solution that's affecting our measurements. So standard addition is a way to account for this and lets us get around this issue. But this is something that's a common feature in many different ion selective electrodes, including pH electrodes. All the different types of electrodes have this that you need to worry about. This is just one of the downsides of ion selective electrodes. There's a lot of good things about them, but this is one of the things you have to worry about.